Yeah, hi everyone. My name is Uri Bones, as Baxter mentioned. And this will be a brief introduction to Elasticsearch, so you all know what Elasticsearch can do for you. Again, it's quite a brief one, so for more details, you'll have to go to the website and check it out. Elasticsearch is a multi-tenant, real-time, and distributed search and analytics engine. It's an Apache 2 licensed open source project, and it's been around for in production over 2 years now. We have more than 2 million downloads, averaging roughly around 200K downloads a month, and it's backed by Elasticsearch, the company. Our company provides professional services around the project, ranging from training, whether on-site or public, consultancy, and production support. So what can Elasticsearch do for you? The first thing, as you might guess from the name, it can do unstructured search, typically known also as free text search. So things like, for example, if we have an index holding companies, we can find all companies in the search market, where search is a search keyword. It can also do structured search, and this is a typical query that you might recognize from databases like Couchbase. So, for example, find all companies founded since the year 2000. The third thing that Elasticsearch is built to do is to provide you analytics. So things like find the average annual revenue of all companies, but the real power comes when you combine all the three together, and you can do things like find the average annual revenue for all companies founded since year 2000 within the search market. And all of this is done in near real-time manner. And the near part basically defines a threshold that defines how quickly a document can be searched and analyzed. By default, by the way, this threshold is 1 second. Elasticsearch is distributed, as I mentioned, and it's good to set some terminology in place. So when you start an Elasticsearch instance, you typically refer to it as a node, and multiple nodes can form a cluster. A cluster manages indices. A cluster is very agile and is self-managing. Every index has certain distributed characteristics, and the cluster, the Elasticsearch cluster, makes sure to maintain these characteristics and also make a proper use of all the nodes in the cluster. When we talk about the index, an index can be seen as a collection of documents, a named or identified collections of documents. It was built and was designed to support both small and large scales data sets. So in general, when we talk about scale, we can talk about data volumes, in which case Elasticsearch can split an index into multiple shards and then distribute the documents that you're indexing between these shards. And when it comes to loads and high availability, each shard can have 0 or more replicas. So it's best to perhaps illustrate how this works in a nutshell. Let's say that we're starting a first node, Elasticsearch node. Then we want to create an index. In this case, we're creating, again, a company's index. We specify the number of shards this index will have and the number of replicas of each shard. So the total number of shards, or in general in the system, will be 4. The first thing that Elasticsearch will do is allocate the shards, or what we like to call the primary shards, on the first node, and that's it. It will not allocate the replicas on this shard because it will not provide any high availability if we do both replicas and primaries on the same node. At a certain point, you might want to add another node to the cluster, in which case Elasticsearch will pick it up, and again, we'll try to make best use of all nodes in the cluster. And the first thing that it will do, it will move one of the shards, one of these primary shards, from node 1 to node 2. But also, it will try to confirm to the number of replicas that you defined and allocate the replicas accordingly. And again, note the replicas and the primaries are allocated on separate nodes to support the high availability factor that you define. So you have an index, and obviously you want to index data into it. Let's quickly see how you do that. A document in Elasticsearch is a JSON document, and that serves a very natural fit with Couchbase. The first thing that you do, you have to specify to what index you want this to index this document, and the type of the document. In this case, the type is company, and the ID, uniquely identified, identifying the document that you're indexing, and the body of the request will be the document itself. Again, this is a document, JSON document representing a company. When you're indexing, your client can choose any of the nodes to execute this operation. In fact, every API that Elasticsearch supports can be executed on any node in the cluster. In this case, we choose to execute this indexing on node 1. The first thing that node 1 will decide is what shard this document needs to be indexed at, using a consistent hashing function. And in our case, it will choose shard 1. And the first thing it will do, it will index it in the primary shard. After it was indexed in the primary shard, it will replicate the document to all the replicas of this shard. You have indexed your documents, and now obviously you want to search on it. So as mentioned, the first thing the Elasticsearch does is unstructured search, free text search, if you will. Elasticsearch has very extensive and powerful query DSL in the form of JSON. And here we're searching, again, the company's index. And if you can see, in this case, we're using a query of type match. And we're searching the search keyword on the overview field in the document. You can also add a structured search to it, and by which effectively will narrow the searchable document space based on some criteria. In this case, we choose to search the documents, only those documents that were founded from year 2000 on. The return results, this is how it looks like, and there are several fields that might be of interest. First, the ID. You'll get back the ID of that document. The score indicating how well did the document match the query that you specified. And Elasticsearch, by default, will also return the source of that document. In the integration, as you will see later on, with Couchbase, this field is disabled by default, but it might be interesting to consider enabling it to support some functionalities, as we'll discuss later on. We're not going to go through all the query DSL and the different types of queries that you have, but again, it's quite an extensive list of different types of queries. Like you can compose queries out of Boolean queries and do phrase or proximity queries, and the same goes with filtering. You can filter in different ways: range, Boolean filter, geodistance, and so on. The third thing that Elasticsearch, as we mentioned earlier, does is analytics, also known as facets. Analytics enable you to slice and dice your data, and while doing that, compute aggregations over the different fields in the document. This is done across all documents that match a query or match a filter, and it needs to be done on all the index fields. And all of these aggregations are done in near real-time manner. And again, this is one of the unique propositions that Elasticsearch has, because a lot of the analytics tools out there nowadays require to do sort of batch processing and offline aggregations over big data, while Elasticsearch does that on query time. Navigation analytics. Analytics is often used as navigation aid. So here we see a hotel booking website, which use analytics and facets on the left-hand side of the screen to help the user narrow their search space. But it can also be used to build analytics dashboards. What we are looking here right now is Kibana, or the new Kibana that we're building. It's a tool that lets you build analytics dashboards on the fly by just effectively deciding which type of statistics you want to show over your data. A lot of times, and people don't realize it, Elasticsearch is used solely for analytics and without any incorporating free text search at all. Basically, using Elasticsearch purely as an analytics engine and not as a search engine per se. How would you go about it? So again, this is just a small example. Assuming that you're indexing company revenues, you can produce a breakdown of all the revenues over the years and get statistics like the average revenues per year for the companies. Again, as you can see, it's part of the query, it's part of the search request, so it will do the aggregations over all those documents that match the query. As a response, you'll get back very simple and intuitive response where you can basically just take as it is and drop it and use any open or closed, whatever you like, charting library and display these statistics as charts. And there are many, many different types of analytics that Elasticsearch supports out of the box. We're not going to go, again, into all of them, but you can pretty much mix and match different types of analytics together with your search to build really sophisticated dashboards and incorporate them in your systems. There's much more to Elasticsearch. Obviously, Elasticsearch comes with a lot of default behavior, but you can really fine-tune and have fine control over how documents are treated in Elasticsearch, whether they're indexed or stored, how the text analysis for the free text search is being applied. We support relations between documents like parent-child, and features like highlighting. And I mentioned earlier that in some cases you would like to store the source, the document itself. Highlighting is one example for that. In order to support highlighting, you will have to have the source also stored in Elasticsearch. Suggests API for type-ahead auto-completion functionalities. Percolator, which enables you to trigger alerts based on criteria that match documents that you're indexing. And we have quite an extensive support for geolocation-based search and analytics, something that is highly, highly common nowadays with all the smartphones on everyone's hand. So, yeah, I'm done with the introduction. I'll move the. If you guys have any questions about Elasticsearch, you're welcome to ask.
Hi, this is Baxter. If you have any questions, feel free to type them into the GoToWebinar panel. Uri, we do have a couple of questions that we can address. First question is from Steven. Will Elasticsearch try to make sure that there aren't too many primary shards on one node? Will it rebalance if there are two primary shards on one node and none on another?
Sure. So in the latest, originally actually, so up to the latest release, we kind of took a very simple approach for a shard allocation, where we just cared about the number of shards per node. Whether it didn't really matter whether they're primaries or replicas. Starting from the latest release, which is 090 RC2, we also take the number of primary shards into account when we do this calculation. So the answer is yes, starting from 090 release.
Great, thanks, Uri. We have another question. This one is from Christopher. Is it more performant to filter rather than query?
Yeah, absolutely. Good question. Filters are definitely one of the most powerful features in Elasticsearch. Typically, yes, it's something that can be outperformed by far queries. The only downside, or it's not downside, but limitation of filters that are not doing any scoring. But if you're building a just analytics engine, or you just need to filter the document set in which you're actually searching on, you should try to use filters as much as possible. Filters are cached, and they can make real differences in the search time.
Great, thank you. We have time for one more question. This one is from Darren. He says, hi, are continuous queries supported?
If you can, I don't understand what continuous queries mean, sorry.
Okay. Darren, if you want to type in further, if you want to kind of clarify your question, we'll address it later on. But for now, let's go ahead and wrap up this portion, and we'll hand it off to Dipti from Couchbase. Keep asking your questions, folks, in the webinar. We'll address more questions at the end of the session as well.
Hello, everyone. Welcome to the webinar. For this section, I'll talk about a brief introduction to Couchbase, but focus mostly on how the integration between Couchbase and Elasticsearch works. So let's get started. Just to give you a brief introduction, Couchbase, as many of you might know, is a distributed document database. Couchbase and Elasticsearch are great complementary technologies. Both use JSON, both are distributed, use consistent hashing, for example, but they're built for different purposes, if you may. So let's take a look at Couchbase and how it works with Elasticsearch. The Couchbase project itself, like Elasticsearch, is Apache 2.0 licensed, and we have both the enterprise and community editions. We support key value use cases and document-oriented use cases. And later today in our example, we'll take a look at how document-oriented use cases work with Couchbase and Elasticsearch to build a custom-driven content portal. There's some of the key characteristics of Couchbase are easy scalability, which is the ability to really grow and scale a cluster, scale up, scale down very easily, click of a button. We'll take a look at the architecture in just a moment. The consistent high performance gives you sub-millisecond response times. And this is particularly something that differentiates Couchbase is the built-in object managed cache, which allows you to get very high throughput, both read and write, with very low latencies. In addition, it's always on, and so your application is up and running as well, which means that all the administrative operations like database upgrades, backups, indexing, compaction, all of these operations are completely online so that you don't have to take down your application for any kind of maintenance. And then finally, the flexible data model. We use JSON as well. With JSON, you get the flexibility of making schema changes very easily and allows you to rapidly build applications and push out your features quite easily. This is something that, like Elasticsearch, people are looking at more and more, trying to use JSON as the data model of choice. Couchbase supports JSON, and we compress JSON on disk. And that actually brings us to the features in Couchbase Server 2.0. So in addition to JSON support, we have incremental MapReduce, as well as indexing and query. And some might ask, oh, should we use Elasticsearch or should we use Couchbase? Actually, the indexing technologies are they're quite complementary. Incremental MapReduce allows you to do some real-time analytics using JavaScript. It's incremental, and so you get answers in real time. And you actually pre-compute your data set or your views before you query. So it's actually quite a different approach compared with Elasticsearch. Elasticsearch is great for doing filters, queries, full text search, and advanced analytics as well. And in the example that we look at, we'll actually see how these two technologies, along with all these features, actually were used together by McGraw-Hill. Next is cross-data center replication, and XDCR, as we call it, is used to replicate data from one entire cluster to another. And it's actually this technology that we use to propagate data to Elasticsearch, and we'll see how that works. In addition, there's a couple of features like built-in clustering. All nodes are equal. There is no replica and there is no master, and so every node manages some active data and some replica data. We have replication within the cluster as well with auto failover, and we talked about the downtime and the maintenance operations. The built-in object-level cache gives you fast access to your documents. And then append-only storage tier, which allows for fast persistence, and online compaction, which allows us to defragment the data on disk very easily while the application is online. We have a great UI and monitoring REST APIs so that you can plug it into your own tools as needed, and as well as a variety of SDKs. So let's take a look at the architecture itself. Every node is equal, and it looks the same, and it has a data manager and a cluster manager. The data manager manages not only the data access, which is key value access via the cache, but also the incremental map reduce operations and the view queries. The cluster manager, on the other hand, manages rebalance operations, replication. It manages failovers as well. And so all the cluster-wide activity is managed by the cluster manager. Given that all nodes are equal, an SDK, a client SDK, we call them smart SDKs, can talk to any node in the cluster and get information about a cluster map, which then tells the client exactly where the document should live, which node it lives on, and which partition it belongs to. But I won't go into all the details of how Couchbase works today. I'll focus on the aspects that help us build the integration and the plugin to Elasticsearch. So the plugin is based on cross-data center replication. And the way the data flow actually works is when a document comes in, the first thing that happens is it gets stored in the managed cache. At that point, we're strongly consistent, so we read and write only from one location within the entire cluster. And so at this point, any other operation can come in and read doc1. Asynchronously, we move documents into the replication queue for replication within the cluster, maybe one or two replicas as you've configured them, and also persist it down to disk, this is what gives you the fast access to data along with the high throughputs. The managed cache is based on Memcache technology, but we have added a lot of algorithms, right, like not recently used, working set management, and so on. And then once it's persisted to disk, it also gets picked up by XDCR, which is the inter-cluster replication, and gets sent over to the other cluster. Now, when you expand this across clusters, it would look something like this. You could have multiple applications that are talking to either data center, DC1 or DC2. Each of them can have active data, so reads and writes are happening on both sides. And you have unidirectional as well as bidirectional XDCR based on your requirements or your needs. So let's take a look at the plugin for Elasticsearch and how that works. In a most simple way, we actually use unidirectional cross-data center replication to constantly move data from your Couchbase cluster to your Elasticsearch cluster. Couchbase handles high volumes of data coming in because of the managed cache, and so it can handle very high ingestion rates. XDCR then dedupes data, particularly if the same document has been updated multiple times, and then sends it over the wire to Elasticsearch. And so when you take a look at the integration itself, this is what it might look like. So you have a Couchbase cluster that is ingesting high volumes of data. It's getting pushed over to the Elasticsearch cluster at the same time. Now, the cluster sizes don't need to match. In this case, there's 3 nodes on one side and 3 nodes on the other. but you can have 4 nodes on one, 3 nodes on the other, depending on your workloads, and the workloads on each of these two systems might look very different. You might need different capacity for each of these clusters. Now, if you see, we have the Couchbase Transport plugin that actually sits on the Elasticsearch side. And so once you install Elasticsearch, you install the plugin, and this is what simulates a Couchbase cluster. So to XDCR, it simply looks like another Couchbase cluster on the other side. And we then translate that information to the Elasticsearch REST APIs and then push it into Elasticsearch for indexing, whether it's full text search or whether it's for faceting and so on. So here's the high-level steps. So prerequisite, of course, is you've got to have a Couchbase cluster and an Elasticsearch. The plugin itself is installed on the Elasticsearch cluster, and so it's pretty simple, pretty straightforward. You can go ahead and install that. We will have a page on our website which gives you the latest links. You set a password because you configure the plugin, and this password will actually be used when you set up XDCR on the Couchbase side. And you install the Couchbase index template that comes along with the plugin. Once Elasticsearch gets restarted, it gets picked up, the transport gets picked up, and once you set up XDCR, you're in business. So data will start getting indexed into Elasticsearch. Now, it's important that you create an Elasticsearch index for your documents, and there's different ways of doing this. You can take a look at some of our documentation on how you can create indexes. Of course, Elasticsearch website gives a lot more information about how to use Elasticsearch itself. Now, in order to configure XDCR, it's really a very easy process. You log into the UI of Couchbase, you click on the XDCR tab, and the first thing you do is establish a cluster reference. All this does is it basically lets Couchbase know that there is another cluster that you want to use for replication, and you provide a host name. So you provide an IP address, and this is where you enter the username and password that you've provided, the password that you just entered when you configured the plugin. That's step one, and then step two is simply to pick what bucket in Couchbase you want to replicate to Elasticsearch. So in Couchbase, a bucket is equivalent to a database. So you can essentially have an Elasticsearch index at a bucket level. If you have multiple buckets, you can decide on which buckets you want to establish the replication on, and which ones you want to index. And so here, if we pick our sample bucket, we pick the Elasticsearch cluster, that's the reference that we just created, and then we use the index name as the target bucket. This sets up XDCR, and this will immediately start replicating data from Couchbase to Elasticsearch. Now, if data is already existing in Couchbase, then it will start streaming immediately. If there is no data in Couchbase, then as mutations start coming in, as your inserts and updates start coming in, that will be pushed over and sent over to Elasticsearch. So once that happens, you know that it's indexing the documents. You'll see this is the older UI, but in the newer UI, you might have more visibility in Elasticsearch. And you'll get to see how many documents have been moved over. Does that count match with the count in Couchbase, for example? So what does a reference architecture look like? How would these systems work together in supporting an application, whether it's a web application or whether it's a slightly more analytical application? And so in your application server, you would have the Couchbase SDKs, along with search and faceting via the HTTP API for Elasticsearch. You would probably store your media content in a separate CDN, a content delivery network, or a media server, for example. But the metadata and some of the content would be stored in Couchbase for fast access, particularly if you're doing streaming aggregations and streaming collection of social media feeds, as an example. You can have reads and writes on the Couchbase side, along with the MapReduce, incremental MapReduce on Couchbase, with our queries over the views on using the SDKs. And then you can also query Elasticsearch via the REST API. On the other side, the document IDs that you get back then can be used to access quickly these documents from Couchbase. Now, in most cases, what we've seen is people want to store data in Couchbase. They want to have analytics and facets and indexing, full text search using Elasticsearch, and they want to be able to have fast access to the data. So you could store documents in Elasticsearch as well, and that's one choice. You can, if you don't store the documents, the Elasticsearch is an option where you can get the document IDs back, as Uri showed earlier. And using the document ID, you can then fetch the document using a GET operation from Couchbase. And so this is from our world. This is what we've seen works well. So the Elasticsearch query comes in, search result gets sent back. You could do a multi-get for fast access, and you get the results back. So this way, you have, particularly for an interactive application, if it's not an analytics application, this would give you the fastest access to your documents and the results. There's a lot of different use cases. This is more for Couchbase, but today we'll focus on content and metadata stores. And this is one of the use cases where we've seen a combination of Couchbase with Elasticsearch works really well. And one of our customers, McGraw-Hill, had performed an extensive POC using Couchbase and Elasticsearch. And so let's take a look at the details for this use case. Another use case that we've seen this combination being used well is for the third-party data aggregation. And this is typically if you're getting feeds from social media, Twitter, Facebook, and you want to create a platform to store all this information. JSON is a great format for that. You need to be able to handle high-speed ingestions, and that's where Couchbase shines. You could create incremental MapReduce for some of the analytics, but then have Elasticsearch do search as well as additional analytics like faceting. So here's the use case for a content and metadata store, and this is something that we've seen document databases being a great fit for. Elasticsearch as well is a great fit for this type of a use case. And so the types of data that we see users storing in Couchbase, for example, is content metadata. Metadata is extremely heavily accessed, and so it's the most accessed part of the application, which needs fast, low latency access. And so it makes it helpful to store it in Couchbase for that low latency access. Content like articles, text, maybe ebooks, digital content, things like that. Landing pages for websites, we've seen that used as well. And then in terms of the application requirements, what we've seen is just being able to flexibly handle large types of content. So different kinds of schemas, every document might look different, and so JSON becomes a great format for it. Need fast access to content metadata, as well as the content in some cases. Need access to full text search across the entire data set, and something that scales out horizontally so that as more content keeps getting added, you can then scale out your system, whether it's Couchbase or Elasticsearch, to meet the demands. So McGraw-Hill Education Labs are building a self-adapting learning portal, and this is built using a Couchbase and Elasticsearch backend. And let's deep dive into the use case. Take a look at what the data model was, or the document model was, which features of Couchbase were used, which features of Elasticsearch were used, and how the system worked together end to end. So the problem that they were trying to solve specifically was that as learning and students move online for for information, for reading all kinds of materials in large numbers. They were looking to build a very, very interactive learning environment where they could support all these aspects. So they wanted to support 1 million users, for example, and maybe millions, tens of millions, use a lot of their content. A lot of this content was unstructured. It was, in some cases, third-party content, like the BBC content, as an example. They wanted to include open content, Wikipedia, for example, and they wanted to support a wide variety of learning applications, so interactive apps, which was a self-adapting system. And so if a user performed certain actions in the portal, the system would be smart enough to give back suggestions or give back or track usage and provide help to the students. So that's the idea essentially for the portal. So what they were looking for was a backend for delivery in the cloud. So there were a few things that really stood out to them. Scaling, so being able to handle spikes in some cases, being able to support multiple sources, being able to support low latency access, particularly for stats, metadata, and some content, full text search and analytics, and content ranking and recommendations as well. And they had experimented with a wide variety of databases, analytical systems, and so on, and other enterprise search servers as well. But they came to us and said, we think Couchbase and Elasticsearch would be a great fit for this backend. And so that's what they decided to pick. The stack itself looked like this. So the technologies that were used were Couchbase to store for OLTP as well as an OLAP database. Used Elasticsearch as a search engine and a recommendation engine. Middleware, they completely built their own middleware, their middle tier for security, for DRM and all the other access that they needed to manage, and had a front end of Ember data. So this is for a very, very great user experience on smart devices and so on. So that was the technology that was used for the portal itself. There were several techniques used, like document, starting off with document modeling, actually using storing metadata and content. They used views for content browsing, and Elasticsearch for the search queries. So search queries and relevance-based boosting, user profiles, so boosting preferences and query results based on some other parameters. And then they stored real-time content updates as well as events. So event logging for offline analysis. So they had one OLTP cluster, they had one OLAP cluster, and on both sides they were using Couchbase and Elasticsearch. So in terms of the end-to-end workflow, they were storing full text articles and metadata in Couchbase. So metadata, for example, for images or videos or even really large pieces of text. Next, the user logs in, and the preferences are calculated based on how many times a user accesses a video, for example, and how many times the user accesses a specific kind of content, which means that the user would prefer that kind of content in searches, for example. And then Elasticsearch would constantly accept all the updates for the content as well as the statistics. And a combination of the user preference stats was used for custom relevancy scoring. The stats were accessed from Couchbase, and then the stat was then used for custom scoring on the Elasticsearch side for personalized search results. So in terms of the data model, here are the three buckets that they actually, I think this is only a subset, but probably the most important buckets that they use. The content metadata bucket itself, or you can think of it as a database, was used for all the metadata for all the objects, for the media, and so on. This included tags, who the contributor for the article was, what the type of information was, and so on. And it included a pointer to the media itself. So the media, which would be maybe stored on a CDN or S3 or some other media store. The user profiles stored information about the user, standard information you might expect, but also statistics about how many times a specific type of document was accessed. And this would then be used to customize search results on the Elasticsearch side. And then finally, content statistics itself. So every time a piece of content was accessed, the metadata was updated. And so this was used to determine popularity of content across the entire set of data, and again used to boost the Elasticsearch results on the ES side. So in terms of the portal itself, things like top contributors or top tags, they like the idea of using incremental MapReduce, given that it was fairly lightweight, to come up with this content. And so Couchbase views were actually used for some of this information. And then Elasticsearch was actually used for the content ranking. So the search box, along with the advanced search options, boosting, so content popularity boosting as well as user preference boosting, were using Elasticsearch for the application. Now let's take a look at an example of how what the data actually looked like and how the boosting worked. So in this case, let's say this is an event, right? It's an event that's logged in Couchbase. So the JSON is stored in Couchbase and then gets on the Couchbase cluster, and you have information like what the document, what kind of access it was, who the user is, what resource was being accessed, and when, right? So these are the important questions that you probably want to answer with event logging and to come up with some analysis for it. And so once this information was collected, Elasticsearch was then used to do boosting. So in this case, we see, So in this case, we see the boost that's being used is user video preference, for example, and this was this was the slider, if you may, to kind of set the preference slider for the user, and in terms of whether you want to boost this based on the user preference or whether you want to boost this based on popularity. So you could either turn both off, you could turn both on, or you can have a weighted proportion of these two criteria. So in this case, let's say video was the type that was used, and that would then be used to boost the results higher than the other results. And then custom scripting was used. So here you see that you have the doc popularity, which is calculated in Couchbase, dot value, and then the average popularity was used along with the popularity that was set for the slider. That's the weight for this specific characteristic, to come back with customized results. So in terms of the combined algorithm, this is what it would look like. So you would boost user video preference, for example, because turns out the user prefers video content to text content or audio content. And in addition to that, you boost results based on the score, which can be calculated using popularity of the content itself. And so using a combined algorithm like this on the Elasticsearch side, with statistics which are gathered from Couchbase, you could come up with a completely customized platform for content delivery or for analytics and so on. And so this is kind of the full kind of frame for the POC. This is what it looked like. There were, you have information about how much content you have. You can do updates on tags, and all the CRUD operations happen on Couchbase, given that they needed to scale to 1 million users. And Couchbase views, along with Elasticsearch for queries and recommendations, were used for the backend for this platform. This was a proof of concept, and actually the code is available. It's open source. It's available on Couchbase Labs learning portal. So if you're interested, you can actually go ahead and take a look at the code, take a look at how the boosting actually works, how you can access the statistics from Couchbase, and then boost the queries on the Elasticsearch side. With that, I'll open it to question and answer. It's now a good time to type in your questions if you haven't already done so.
Great. Thanks, Dipti. First, we wanted to hand it back to Uri of Elasticsearch for some clarification around the question earlier about continuous queries. Uri, do you want to address that question?
Sure, Baxter. So yeah, so the idea is that if the meaning is to have queries that are executed every time that the document is being indexed into Elasticsearch, and then the answer is yes, and that's sort of the percolator feature that I mentioned earlier. It enables you to register queries. It's kind of, we treat it as a reverse search. Instead of storing or indexing documents, we're registering queries, and then what you can do is percolate documents through those queries, and this can be done also at index time. So whenever you're indexing a document, all these queries that we register are being evaluated on the documents that you're indexing, and as part of the indexing response, you'll get back the IDs or the list of ideas of the queries that match each document. So if the intention with continuous queries to have this kind of functionality, the answer is yes.
Great. Thank you, Uri. We'll now address some further questions.
So a question from Stephen. Question is, do the documents in Elasticsearch look exactly like the ones in Couchbase, or is there some sort of ETL that happens along the way? So Stephen, given that both Couchbase and Elasticsearch store JSON, the documents would look exactly the same. You have the choice on the Elasticsearch side to either store the document in Elasticsearch or just have it indexed so that it's a part of the Elasticsearch index, but you don't store it twice. So if you don't want to duplicate data, you have the option to just index the document, and then the document would be thrown away on the Elasticsearch side. Of course, when the next mutation comes in, the index will get updated based on the new data and so on. So that's how the end-to-end would work. Now, one thing to point out is that features like highlighting, for example, in Elasticsearch, probably need you to store the document. They need the source data and that needs to be stored in Elasticsearch. So that's something that you should think about, is what the features of Elasticsearch you might need, and then based on that decide whether you want to store the documents in both the data sets, both the storage systems, or just in one. A question about expiries and TTL. So this one is from Michael, and the question is, what happens if you store a document with a TTL, which is an expiry in Couchbase, and it expires? Does it persist in Elasticsearch after the TTL expires, or does it kill the document there as well? So the way it works in Couchbase is an expiry actually gets translated to a delete, and the delete will get propagated to the Elasticsearch side, and it will push a delete for that document. Now that said, Elasticsearch also has the concept of expiry, and that's something that you can tune as a part of the template, the plugin template, if you want to have a TTL on the Elasticsearch side as well, so that it automatically expires data. So that's how it works with expiries. A question about data centers and how to set up replication. So this one's from Marcin. Can we set up more data centers for replication, not to lose this functionality while we are setting replication to Elasticsearch instead of another data center? Yes. So if you have a bucket that you want to establish disaster recovery or maybe an active standby in another data center, let's say you have a San Francisco data center and you have a New York data center, and the buckets that live in San Francisco, you want to make sure that you have a hot standby, for example, in New York. Then you can set up 2 replication streams in this case. Let's say the bucket name is called content metadata. Then in this case, you will create, as I showed earlier, you will create 1 cluster reference for the data center that you want to establish your hot standby in, and then you will create another cluster reference for the Elasticsearch cluster that you want to use on the side within the same data center probably. And in this case, you'll have 2 cluster references. Next, you set up replications. You set up 2 replication streams. So for content metadata, the source bucket will be content metadata, and the target cluster for DR will be your New York data center with a target bucket, let's say content metadata New York. And then you set up another replication with the same source bucket and the same source cluster. The remote cluster would be different. In this case, you would type in Elasticsearch, which is the second cluster reference that you've created, and then use the index name as the bucket name. And this way, you'll establish 2 replication streams for a Couchbase bucket. One for DR, which is for if your data center goes down, and then the second one for Elasticsearch. So a more generic question next about NoSQL in comparison with a relational database. And this question is from Nicola. The question is there any risk on storing user data in general, username, passwords, preferences, etc., in a NoSQL environment instead of a relational database environment? NoSQL offers a lot of benefits over relational. Of course, relational technology has been around for a long time, and you get a lot of benefits, particularly on the transactionality basis for security, if you need advanced security and so on. But we have a lot of large enterprise customers who have actually specifically used Couchbase to create a distributed user profile store that spans multiple data centers. And this is one of the popular use cases actually for Couchbase. Because of the low latency access, you can have millions of users that are accessing the profiles. It could be a social game. It could be a very popular cloud store that you need to store these user profiles for. And high throughput as well is supported. And so this allows you, along with replication, high availability, and cross-data center replication, allows you to create a very, very stable platform for a distributed user profile store. Now, if you have specific SLAs, if you have durability requirements, there are various options that can be tuned accordingly based on your use case. All right, we have time for one last question, and then we will conclude our webinar. How long, so the question is from Arvino. How long does it take for JSON data that is written in Couchbase to be replicated to Elasticsearch? Does this happen in seconds or minutes? And what would be the recommended network bandwidth to achieve best performance? So it depends. It depends on a lot of factors. What we have seen is if you have a read-heavy or a mixed workload, it could be milliseconds, or at most a second if you have a large disk write queue in case of peak loads or where you have heavy writes on the system. But it really depends on disk. So this is in the case of spinning disk. Of course, if you have SSDs or flash, it would be much significantly faster. And in our next version, for example, in 2.02, we are further enhancing our persistence tier to make it completely multi-threaded. So we have more than 2 readers and writers per bucket. And so we added a threaded pool where we have multiple readers and writers writing to disk, which will significantly improve even persistence to disk and then sending it over the wire to Elasticsearch. Now, typically in terms of the bandwidth, Elasticsearch, whenever you have a text search or a search and analytics system that sits next to your OLTP database, they typically sit next to each other. So they're typically in the same data center, within the same LAN, And so the bandwidth typically does not become a problem or does not become an issue. You probably need to plan out bandwidth in terms of capacity and so on for XDCR if you are planning to have disaster recovery set up across data centers. And in that case, latency across the wire to another data center may have an impact on, will certainly have an impact on how long it takes a document to get from one data center to another. We have customers with 10 gig interconnect all the way to 40 gig interconnect, and so this is across data centers. And so it depends on your setup, it depends on the hardware, but hopefully this gives you an idea of how it works and what can be used to optimize this behavior. All right, it's the top of the hour. Thank you very much for joining us today. Feel free to reach out to us if you have questions. And if we haven't gotten to your question today, we'll try to get back to you directly as well. The slides and the recording will be available and sent out to you shortly. Thanks, everyone. Have a great day.